wide bandgap devices, especially silicon carbide and gallium nitride, promise to bring about the next revolution in power electronics. This series of videos on wide bandgap devices for power converter designers aims to illustrate the superior characteristics and performance of wide bandgap devices. The target audience is power converter designers and power electronics students. So it's certainly not intended to be a detailed discussion on the complex semiconductor physics of the wide bandgap devices. Rather, the focus will be on understanding what the superior characteristics are and how they can impact the efficiency and power density and performance of power converters, and how to design converters exploiting the promise of wide bandgap devices. Now, semiconductor level analysis of say diodes and MOSFETs, their operating principles and structures will be discussed only to the extent that they are needed to understand the superior features of wide bandgap devices. This video is part 1 of the introduction, where we establish the switch as the essential critical building block of all the power converters. Then look at the benefits and challenges of high frequency switching, and mostly compare the ideal switches with real practical switches, especially those made of silicon material, and use that to establish the requirements, often conflicting requirements of a high performance switch. We'll also look at the switching waveforms of a simple boost converter example to illustrate these concepts, and later in part 2 we'll look at some numerical examples of loss calculations, look at some data sheets, and this will lead into the potential of wide bandgap devices for a high performance switch. Power electronics is a key enabling technology with ubiquitous applications ranging from renewable energy interface, solar and wind energy, automotive applications, especially hybrid and electric vehicles, switch mode power supplies, SMPS and UPS for all electronic equipment, and in modern data servers, motor drives with applications ranging from residential appliances to robotics to large industrial motors, power flow control in large electric transmission and distribution systems, especially the emerging solid state transformers, lighting and mass transportation. The power semiconductor switch is obviously a key component that majorly impacts the performance of the converter, and therefore that is the subject of this series of videos. A quick look at the popular power converter topologies, or in fact any converter topology. For example, the various DC-DC converters like the buck and the boost or Chuk converter, the half-bridge converter topologies, the full-bridge converter used in DC motor drives and single-phase inverters, three-phase inverters used in large motor drives, UPS, and even the more complex topologies like the multi-level converters or matrix converters. All of them, as you can see in these figures, all of them involve the use of multiple switches. What is shown are they belong to the category of voltage source converters, but even the other types like the current source converters also employ multiple switches. Therefore, the switch is really the critical building block of any converter. Depending on the application and circuit configuration and the location and role of the switch can be either a passive device, a diode as shown, or it could be an active controlled device as shown here. So at present, for much of the applications that we are considering, the popular choice for the controlled switch is either an IGBT or a MOSFET. And therefore our focus in this series of videos will be on these three switches. In fact, the device has been the main driver of the evolution of power electronics. Power electronics started with thyristors and with line frequency switching or force commutated switching at a few hundreds of hertz. Then came the bipolar junction transistor, which really started the era of switch mode power electronics and achieved switching frequencies in the several tens of kilohertz. Then the MOSFET completely revolutionized high frequency switching, pushing the frequencies into several hundreds of kilohertz and with excellent efficiencies. Then IGBTs pushed the application to the high voltage and high power areas, even though the frequencies are not as high as in the MOSFET, but they were able to extend the applications well into the kilovolts and megawatt power levels. And the wide bandgap devices, they are expected to further revolutionize the field of high frequency switch mode power electronics at high voltages and high power levels. This is a circuit configuration of a typical single phase solar PV inverter. So you have a DC-DC stage which does the high frequency transformer isolation, maintains the DC link voltage at a value suitable for grid interface at say 240 volts. It also does the maximum power tracking function from the solar arrays. The next stage, the DC to AC inverter, does the DC to AC conversion and controls the line current injected into the grid. Now, this is an application that can significantly benefit from the use of wide bandgap devices to push the frequencies from the currently used 10 to 20 kilohertz to about 200 kilohertz, thereby achieving a significant improvement in the power density, meaning much smaller size and weight, which are important metrics for a PV inverter, as well as reduce the losses by like more than 50% of the current solutions. The size reduction comes from the reduced size of the transformer with frequency, as well as the reduction in the filters, the LC filters, the output, as well as the boost inductor of the DC-DC stage. They come down in direct proportion to the switching frequency. So I'm going to show a simulation that illustrates the decrease in the filter required as you increase the switching frequencies. This simulation shows just a DC to AC stage of the PV inverter, a 400 volts DC to a 240 volts RMS grid with just a single L filter. Now initially let me keep the frequency at 20 kilohertz corresponding to the current inverter designs, and let's look at the inductor current waveform. So I'm showing the grid current. The green waveform is the current injected to the grid, and the red waveform inside that is the desired current reference. So you can clearly see the high frequency switching ripple in the inductor current, and by going to a higher switching frequency, we can significantly reduce these values. Okay, so I have saved the waveform corresponding to 20 kilohertz. Let me now go ahead and change the switching frequency to 200 kilohertz and look at the line current, the grid current, and compare that with the 20 kilohertz case. Okay, so you can so the blue waveform is the original 20 kilohertz line current waveform, and you can see this small green waveform is still simulating. That is the line current with the higher switching frequency. So let me just momentarily not show the previous waveforms. Now you can see the actual line current is almost free of high frequency, very small high frequency ripple. Only if you zoom in, you can see the high frequency ripple here. So let me now show both of them together. Okay, and then zoom in somewhere here. You can see the ripple is significantly reduced. You can look at the numbers and see that it's really 1/10 of the 20 kilohertz current ripple. So what this means is that for a given THD specification, the total harmonic distortion specification, we can reduce the size of the output filter by almost 10 times to meet the same specification. So that results in a large savings in the filter size and cost. The lower waveform shows the PWM waveforms applied to the filter end, and you can see the 10 times higher pulses in the second case compared to the original, the blue waveform. So the motivation for high frequency switching is clear. However, higher switching frequencies result in higher switching losses. So in order to understand that, we should look at the characteristics of real switches versus ideal switches, and then try to understand the switching loss phenomenon as well as other sources of losses. To understand the important characteristics of real practical switches and their impact on converter performance, let's look at the switching waveforms of a boost DC-DC converter as an example. So here is a schematic of the boost converter, this control switch and this passive diode. During this on interval, when the switching signal is 1, the switch is on, and when the switching signal is 0, then the switch is off and the diode conducts. And here is the input-output relationship of a boost converter. This is the equivalent circuit during the switch on interval, this interval. The switch is on, therefore it is represented as a short circuit for an ideal switch, and the diode is open circuited, shown here. And during this period, the current and therefore the energy in the inductor is built up, and this is the equivalent circuit during the off interval. So the switch is turned off, represented by open circuit, and the diode is on, and that is represented by the short circuit here. So during this interval, we can show that the voltage across the inductor is negative. So the current decreases, therefore the energy decreases, and what happens is the energy stored in the inductor is fed to the load and the output capacitor combination. Looking at the detailed switching waveforms, the first waveform is the control signal, the switching signal applied to the gate. So this can be the input to the gate driver IC, on interval and off interval. And this is the waveform of the inductor current IL. So during the on interval, the current rises. During the off interval, the current falls. So what is of importance is the current and the voltage waveforms of the main switch, the MOSFET, as well as the current and voltage waveforms of the passive diode. So these two waveforms correspond to the MOSFET or the controlled switch waveform. The first, the blue waveform, is the current waveform. So when the device is on by this control signal, the current in the device is exactly same as the inductor current, and when the switch is off, the current is 0. Similarly, the voltage across the switch when the device is turned on is ideally 0, and when the device is off, it supports the maximum voltage, which in this case is the output voltage. This magnitude is VO. Then the next two waveforms correspond to the diode current and the diode voltage at the bottom. The diode is forced to conduct when the switch turns off at this instant by removing the gate drive, and then it takes up the inductor current at that instant. The diode voltage was same as the output voltage V out when the switch was conducting. Clearly, when the switch is on, the voltage across the diode is V out, and when the diode is forward bias and is conducting, then ideally the voltage across the diode is 0. We will look at the non-idealities in the later slide. So these waveforms have been drawn corresponding to an ideal switch as well as an ideal diode. So the assumptions here are an ideal switch and diode entail 0 forward voltage drop when the device is conducting. So that will be this duration for the switch and this duration for the diode, and therefore ideal switch corresponds to 0 conduction loss. Also, we assume that the transition times for example, for the current to go from this peak value to 0, as well as for the diode current, and for the voltages of the switch to go from 0 to the full rated blocking voltage, those transition times are 0. Therefore, the switching losses are also 0 with the ideal switch and diode. Next, we will compare this situation with one where we use real practical devices. In this particular slide, I'm going to look at the forward voltage drop and the resulting conduction loss. So let's zoom in this on interval, the switch voltage, the MOSFET voltage waveform. If I really zoom in, I can see that this ideal switch waveform, it is exactly 0 when the device is on, whereas a real switch will have a significant forward drop. So there will be a constant drop plus a portion corresponding to the resistance times the current. So the values for typical high voltage switches are in the 2 to 3 volts range, and that results in conduction losses. Similarly, if you zoom in this region for the diode drop, we can see that an ideal diode, of course, has a 0 drop across it, whereas a real diode, so I've been drawing the diode voltage as the cathode to anode voltage. So when the device is off, it is supporting a large positive voltage, and when the device is conducting, the voltage across that is a small forward drop of the diode. Again, for depending on the type of the diode, the voltage can vary, and it's typically about 2 volts for a high voltage ultra fast diode. So the forward drop in both the control switch as well as the diode result in conduction losses. So this is the conduction loss in this switch. Ideal switch has no losses, whereas the real switch loss is the forward voltage drop times the device current. Similarly, for the diode also, during this interval there is a conduction loss, and that is equal to the forward drop times the diode current. The other important source of losses, even more significant for high frequency application, is of course the switching losses. So let's zoom in near the switching transition instance and understand the switching process and the switching losses. So I zoom in near to begin with at the turn off instant. This is when the gate drive goes from high value to low, and the zoomed in portion are shown here. So this is the control voltage coming from high value to 0. The inductor current in that small interval could be tens of nanoseconds or hundreds of nanoseconds depending on the device. So in that short period, the inductor current is almost a constant. Zooming in on these 4 waveforms, the 2 voltage and 2 current waveforms of the MOSFET and the diode. So for some time after the gate drive control signal is removed, there is really nothing happening. So this is when, for example, the gate voltage is coming from say 15 volts to a lower value corresponding to the required gate voltage for the given current. So no transitions happens at this period. So this is part of the delay time. So during this instant, there is really no losses. So after that period, the gate voltage has become low enough for some of the transitions to occur. So the first change is the switch current cannot begin to drop instantaneously, because the inductor current has to be supported either by the switch or the diode, and the diode can begin to conduct only after its voltage has become 0, or once it begins to get forward biased. So the first response is for the switch voltage to rise. So it rises as shown here. Correspondingly, the voltage across the diode comes down, and once it reaches 0, then the diode can be forward biased and the diode current can increase. So at that point, the diode current increases and the switch current can begin to come down, and it comes down and reaches 0 at this interval. So this duration is called as the TF, the fall time duration for the switch, and the diode current has risen to the full value of the inductor current, and Is is 0. Okay, so in the process there is during these two sub intervals, if you look at this interval, we have across the switch a large the full current, rated current, and the voltage is rising, so there's overlap of high voltage and high current, results in very large instantaneous power loss. And in the third interval, we have the full rated voltage blocked by the voltage, and the current is falling from its rated value towards 0. So once again you have high instantaneous power loss. So this corresponds to the turn off switching losses. And many times the data sheets give the energy loss for a given current and voltage during a turn off, and so that is this value. Next, let's look at the other transition interval, which is the switch turn on transition in this region. So if you zoom in on this region, this is when the gate voltage goes from low to high, and the device is to be turned on. Okay. So once again, here's the control voltage. The inductor current is assumed constant in that small transition intervals, and these are the two voltage and current waveforms of the switch and the diode. Okay. So similar to the previous case, there is a small instant when there is not any transition happening. This is when the gate voltage is rising either from a negative voltage or from 0 towards the threshold voltage, and after it has reached that value, then the first response is for the switch current to increase. So it increases with the rising gate voltage, and correspondingly the diode current also simultaneously decreases, because the sum of these two currents should be equal to the inductor current. So at this instant, when the diode current has reached 0, or the switch current has reached the same as the inductor current value, the ideal diode should turn off at this instant. But a real practical diode has the reverse recovery phenomenon, whereby the current continues in the negative direction till all the minority carriers are either recombined or swept by the reverse current. So this is the this peak value is the peak reverse recovery current, and the area under this negative portion is the reverse recovery charge. So during the duration when the diode current is conducting up to this peak negative current, the diode voltage is close to 0, and therefore the switch voltage is at its rated value. So only after this instant, after this reverse recovery process, the switch voltage can begin to fall, and so clearly we have an overlap of large current and full rated voltage during both this current rising interval and during this voltage falling interval, once again resulting in very high instantaneous turn on switching losses. So once again we can get the turn on energy loss from the data sheet for a given current and voltage and for a given given diode characteristics. This is the energy lost per transition, in this case the turn on transition. We can add this to the turn off transition energy, and the switching frequency times this total energy loss is the average switching power loss in the device. So obviously higher the switching frequency, higher the switching losses, and it becomes a challenge to achieve good efficiency at these high switching frequencies. So we will end part 1 at this point, and in part 2 of the video we will look at some numerical examples of conduction and switching losses with some practical devices, and that will lead into the potential for high performance with wide bandgap devices.